All right, so ready to dive into some pretty fundamental computer science today.
Absolutely.
We're talking binary search trees,
Love it.
which I think a lot of people, even if they don't know the term, they kind of get the concept.
Yeah, for sure.
It's basically like, how do you store data in a way that's super organized that you can actually get to it quickly?
Right, like a really efficient filing cabinet.
Yeah, exactly. A
Got it.
digital filing cabinet.
That's a great way to put it.
And the cool thing is, it can act as both a dictionary.
Mm.
So, like, I want to look up a definition or I want to see if a word exists. Boom, it's right there.
Right.
But it can also act like a priority queue where it's like, all right, what's the most important thing I need to deal with right now?
Exactly. And that's what makes them so powerful, this ability to work with data in a very dynamic way.
Mm,
We're talking about these really important operations like searching for specific information,
right.
finding the smallest, the largest values, figuring out what comes before or after something in a sorted sequence.
Right. Like moving through the data in order.
Exactly. And of course, adding new data and removing data.
Right. The classic insert and delete.
Exactly.
So one thing that's really key here is that how fast these operations are really depends on, like, the shape of the tree.
Right. The height of the tree is crucial.
Yeah. And the best case, and this is what everyone wants, is when you have this perfectly balanced tree.
Yes, a nice symmetrical structure.
Yeah, like a pyramid or like, one of those perfectly stacked,
Yeah.
like a display of fruit at a grocery store.
I love that analogy. Yeah.
All right. And in those cases, if you have, let's say, pieces of data, it's crazy how fast you can do these operations.
Right. It's incredibly efficient.
Yeah, it only takes logarithmic time, which is written as like theta of log n.
Yeah. LGN.
Right. And that, for anyone who's not like deep in the math, that basically means as your data gets huge, the time it takes to do stuff doesn't increase that much.
Exactly. It scales really well.
Yeah. And that's crucial when you're dealing with like massive data sets.
Absolutely. But we also have to be aware of the worst case scenario.
Oh, yeah. Things can go wrong.
Right. Where the tree gets very lopsided.
Mm-hmm.
Oh.
Like it's all stretched out in one direction.
Yeah, almost like a single line of connected nodes.
Yeah, like a chain instead of a tree.
And then the efficiency plummets. You're down to linear time, or N.
And that means for a really big data set, things can get slow.
Yes, it's directly proportional to the number of data points.
Right, so not ideal.
Not ideal at all.
But this is where it gets interesting, right? There are like these clever variations of binary search trees. Like, have you heard of red-black trees?
Oh yeah, red-black trees are fascinating.
They're cool. And basically, they have these mechanisms built in to like keep themselves balanced.
Right, they self-adjust to avoid that worst-case scenario.
Exactly. So they guarantee you're always going to get that nice, efficient, logarithmic time.
Exactly. They ensure good performance, even with a lot of data.
Which I think, maybe we'll do a whole other deep dive on red-black trees sometime.
I love that.
Yeah. But what's cool is that the chapter we're looking at today, it mentions that even if you just build a tree randomly, like you're just throwing data in there, no special order or anything.
Right, just adding things as they come.
The average height of the tree still tends to be pretty good.
Yeah, the expected height is still on the order of log n.
Which is, like, kind of amazing.
It is. It speaks to the inherent tendency towards balance.
Yeah. So even without,
Yeah.
like, all this fancy balancing stuff,
Yeah, right.
in a lot of real-world situations, you're probably going to be okay.
Yeah, especially if the data arrival is somewhat random.
Right, exactly.
So for our deep dive today, I think it's important to really grasp those fundamental principles of binary search trees. We've got this great chapter summary, and we want to give everyone a clear explanation of what they are, how they work, and why they matter.
Yeah. All right, let's do it.
All right, let's start at the beginning. What is a binary search tree?
Yeah, what are we even talking about here?
At its core, it's a hierarchical data structure, a specific type of binary tree, where each point in the tree, called a node, holds a piece of data, which we call the key.
Okay, so the key is like the core piece of information.
Exactly. It's what we use to organize the tree and search through it.
Got it.
And along with the key, a node can also have other associated data. We call that satellite data.
Okay, so like an example.
Sure. Think of a phone book. The name would be the key, and the phone number, the address, that would all be the satellite data.
Okay, so the key is how we find it, and then the satellite data is the actual, like, useful information we want.
Exactly.
Okay, so we have these nodes, but they're not just floating around randomly, right?
No, they're all connected in a specific way.
Okay, how so?
Each node can have up to 2 children, a left child and a right child, and of course, it has a parent node.
Right, so it's like a family tree, kind of?
Yes, but upside down, with the root at the top.
Okay, I can visualize that.
And these relationships are maintained using pointers.
Pointers, like,
Yeah, they're basically references from one node to another.
okay.
So the left child pointer of a node points to its left child, the parent pointer points to its parent, and so on.
Got it. And what if a node doesn't have a left child or a right child?
Then the corresponding pointer is set to NIL. It means there's no connection there.
NIL, that's like null, right?
Yeah, exactly. It indicates the absence of a child.
Okay, makes sense.
Now, every tree has to have a starting point, a top node.
Mm-hmm. Like the trunk of the tree?
Exactly. We call that the root.
Root, okay.
And the tree itself has a root attribute, which is simply a pointer to this root node.
So it's like the entry point where you start exploring the tree.
Precisely. And if the tree is empty, meaning it has no nodes, then the root attribute would also be NIL.
Okay, so it's like, hey, there's nothing here yet.
Exactly.
So we have nodes, we have these connections, but what makes it a search tree?
Ah, that's where the binary search tree property comes in.
Okay, hit me with it.
It's the defining characteristic of a binary search tree.
Okay.
For any node in the tree, let's call it X,
X, all right.
all the keys in its left subtree.
Okay, so everything connected below and to the left of X.
Right. All those keys must be less than or equal to the key of X.
Okay, so everything to the left is smaller.
Exactly. And conversely, all the keys in the right subtree.
So everything below and to the right.
Correct. All those keys must be greater than or equal to the key of X.
Okay, so everything to the right is bigger.
Exactly. And this is crucial. This rule applies to every single node in the tree, not just the root.
So it's like this rule that propagates all the way down.
Yes, it's what ensures the tree is organized in a way that makes searching efficient.
I see. So if I'm looking for something and it's smaller than the current node, I know I only need to look on the left side.
Precisely.
And if it's bigger, I only need to look on the right.
That's the beauty of it. You're constantly narrowing down the search space.
That's super smart.
And here's another interesting thing.
Okay. You can actually have multiple different binary search tree structures that represent the same set of values.
So like different shapes, different arrangements of the nodes.
Exactly, as long as they all adhere to this binary search tree property.
That's interesting. So there's flexibility in how you build it.
Yes, and that flexibility plays into those best case and worst case scenarios we talked about earlier.
Right, the pyramid versus the chain.
Exactly.
Okay, so we understand the structure, we understand the property. Now, how do we actually do things with these trees?
That's the fun part. Let's look at the operations.
All right, what's first on the list?
Let's start with the in-order tree walk.
In-order tree walk?
Yeah.
That sounds kind of fancy.
It's a very elegant and systematic way to visit every single node in the tree.
Visit, meaning like do something with the data at each node.
Exactly, like printing the key or performing some calculation.
Okay.
And it's a recursive process.
Recursive, so it calls itself.
Precisely. It breaks the problem down into smaller subproblems.
Okay, how does it actually work? For any given node, you first recursively traverse its entire left subtree.
So you go all the way down to the leftmost leaf.
Right. Then you visit the current node itself.
So you do whatever operation you need to do with that node's data.
Exactly. And finally, you recursively traverse its entire right subtree.
So you go all the way down to the rightmost leaf?
Precisely.
Okay, I think I get the steps. But what's so special about the in-order part?
Here's the key. Because of the binary search tree property, the in-order tree walk processes the keys in sorted order.
Whoa, really?
Yeah, think about it. Everything to the left is smaller, then you process the current node, then everything to the right is bigger.
So it's like it naturally sorts the data as it goes.
Exactly.
That's super useful.
Incredibly useful. So if you have a binary search tree with numbers in it, the in-order tree walk would print them out in ascending order.
Awesome. And how efficient is this? Like, how much time does it take?
Since you visit every node exactly once, the time complexity is n, where n is the number of nodes.
Linear time, so it scales directly with the size of the data.
Exactly. And the chapter also briefly mentions pre-order and post-order tree walks.
Okay, are those similar?
They're also recursive traversal methods, but they differ in when you visit the current node relative to its subtrees.
So, like, do you visit the node before or after you explore its children?
Exactly. Pre-order visits the node before, post-order visits it after.
Okay, interesting, but we're not going to dive into those right now.
Not in detail. The chapter doesn't focus on them.
All right, so in order gives us sorted output in linear time.
That's a good summary.
Now, what if we want to find a specific piece of data, a specific key?
That's where the search operation comes in.
Tree search, right.
Exactly. It's all about locating a node with a specific key.
Okay, how does it work?
You start at the root of the tree and compare the key you're looking for with the key of the current node.
Okay.
If the key you're looking for is smaller than the current node's key, you know it must be in the left subtree.
Right, because of the binary search tree problem.
Exactly. So you move down to the left child and repeat the process.
Okay, and if it's bigger?
Then you move down to the right child.
Got it, and if it's equal?
Then you found the node you were looking for.
Success.
But what if the key isn't in the tree at all?
Yeah, how does it know when to stop?
It keeps going down the appropriate branches until it reaches a NIL pointer.
NIL, so like the end of a branch.
Precisely. That means you've gone as far as you can and the key isn't there.
Makes sense.
And the chapter also mentions an iterative version of this search called iterative tree search.
Okay, so not recursive this time.
Right. It uses a while loop instead.
So it's just a different way to achieve the same goal.
Exactly. It keeps track of the current node and moves it left or right based on the key comparison.
And it stops when it finds the key or hits a NIL pointer?
Precisely.
Okay, cool. So we have two ways to search.
And both of them have a time complexity of, where h is the height of the tree.
So the taller the tree, the longer it might take.
Yeah, in the worst case, you might have to traverse a path from the root all the way down to a leaf.
Okay, so searching is efficient, especially if the tree is balanced.
Exactly.
Now, what about finding the smallest or largest value in the whole tree?
That's where tree minimum and tree maximum come in.
Okay, those sound pretty self-explanatory.
They are. To find the minimum, you start at the root.
Okay.
And you simply follow the left child pointers.
So keep going left.
Until you hit a NIL pointer.
Okay.
The last non-NIL node you visited, that's the one with the smallest key.
Ah, I see, because everything to the right of it must be bigger, and there's nothing to the left.
Exactly. It's the smallest in the whole tree.
And maximum, I'm guessing, is the same, but going right.
You got it. Tree maximum is the symmetric operation. You follow the right child pointers until you hit NIL.
And the last non-NIL node is the biggest.
Precisely.
Okay, those seem pretty easy.
They are. And like tree search, both of these have a time complexity of,
So again, it depends on the height of the tree. Now, there's this operation called successor.
Yes, tree successor.
What's that all about?
It's about finding the next node in the sorted order of keys.
So, like, if I'm at a certain node, what comes after it in the sequence?
Exactly, as if you were doing an in-order tree walk.
Okay, how do we find that?
There are two main cases to consider.
Right, lay them on me.
The first case is when the node you're at, let's call it X,
X.
if X has a non-empty right subtree.
So there are nodes to the right of it.
Then its successor is simply the minimum element in that right subtree.
Ah, so we just use tree minimum on the right subtree?
Exactly, because everything in that subtree is bigger than X, and the smallest one will be the very next one in the sorted sequence.
That makes sense.
The second case is when X has an empty right subtree.
So it's like, it's as far right as it can go.
Exactly. In this case, the successor is the lowest ancestor of X for which X is in its left subtree.
Okay, that's a bit more complex.
It is. You essentially have to travel up the tree from X until you find a node that's a left child of its parent.
I think I need to visualize this.
Think of it this way. If you've gone as far right as you can in a part of the tree, the next larger element must be somewhere up the tree on the left branch of an ancestor.
Okay, so you go up and then take a right turn.
Exactly, and the chapter also mentions the tree predecessor operation, which is the opposite.
So finding the node that comes before the current node.
Precisely, it's symmetric to successor.
So if there's a left subtree, you find the maximum in there, and if not, you go up the tree looking for a right turn.
You got it.
Okay, so we can search, we can find min and max, we can find what comes before and after a node.
All important operations.
Now, how do we add and remove data while keeping the tree properly organized?
Let's start with insertion.
Tree insert, right?
Exactly. So we have a new node. Let's call it Z.
Okay.
We want to add Z to the tree without messing up the binary search tree property.
Right, got to keep it organized.
So we start at the root and traverse the tree, just like in tree search.
Okay, comparing keys and going left or right.
Precisely, until we reach a NIL pointer.
NIL, so
Yeah.
we found an empty spot.
Exactly. And the node just before the NIL pointer, let's call it Ya.
Yeah, era.
Ya becomes the parent of our new node Z.
So we attach Z to U.
Correct, either as the left child or the right child, depending on whether Z's key is smaller or bigger than Y's key.
Okay, so we're maintaining the order?
Exactly, and then we update the parent pointer of Z's to point back to...
So now Z knows where it belongs in the tree.
Exactly.
Cool, that sounds pretty straightforward.
It is. Insertion is generally less complex than deletion.
Yes, deletion. That sounds like it could be tricky.
It is. Tree delete is the most involved of the basic operations.
Because now we're not just adding something, we're taking something away and potentially creating a hole.
Exactly, and we have to be careful not to break the tree structure or the binary search tree property.
Right, so how do we handle this?
Well, it depends on how many children the node we want to delete has.
Okay, so different scenarios.
The chapter outlines 3 main cases. Let's call the node we want to delete Z.
Z for doomed.
The first case is when Z has no left child.
Okay, what do we do then?
In this case, we simply replace Z with its right child.
Okay, so if it only has a right child, we just connect that child directly to Z's parent.
Precisely, and if Z has no children at all,
then its right child would be NIL, so we're basically just removing Z.
exactly.
Okay, case 1, handle.
Case 2 is when Z has a left child, but no right child.
Okay, so the mirror image of case 1.
Exactly. We replace Z with its left child.
Got it. So those 2 cases are pretty straightforward.
Relatively. Now, case 3 is where things get interesting.
This is where Z has both a left and a right child.
Precisely. And this is where we need to find the successor of Z.
The successor, so the node with the next largest key?
Exactly. And if Z has a right subtree, its successor will always be the minimum element in that right subtree.
Okay. And I remember we talked about how to find the minimum.
Yes, with tree minimum.
So we find the successor, let's call it Yi,
Yeah, good choice.
and then what?
There are 2 subcases here. Subcase 3A is when Y is the direct right child of Z.
So the successor is right there.
In this case, we replace Z with Y, and Y's left child becomes Z's left child.
Okay, so we basically lift you up and reconnect the left subtree.
Exactly. Now, subcase 3B is when Y is somewhere deeper in Z's right subtree.
So not a direct child.
Correct. In this case, we first have to deal with Y's original position.
Okay, that's it.
So Li is the minimum in Z's right subtree. It won't have a left child, but it might have a right child.
Okay,
So we replace U with its own right child.
okay, detaching U.
Right. Then we take U and put it in the place of Z.
Okay, so Yoke takes over Z's role.
Exactly. Ye's left child becomes Z's left child, and Yi's right child becomes Z's right child.
So we're basically transplanting Yi into Z's position.
Precisely. And of course, we need to update all the parent pointers to maintain the correct relationships.
Right, got to keep the connections consistent.
And the chapter actually refers to this process of replacing a subtree with another as the transplant subroutine.
Okay, so it's like a helper function used by tree delete,
Exactly. And it's especially important when the node we're replacing is the root.
because then we need to update the tree's root attribute.
Precisely.
Okay, so deletion is definitely more complex.
It is, but even in the worst case, it still has a time complexity of...
So still dependent on the height.
Yes, the taller the tree, the more steps it might take.
All right, so we've covered all the basic operations.
We've seen how to search, find min and max, navigate in sorted order, insert, and delete.
The chapter also mentions exercises and problems.
Yes, those are great for solidifying your understanding.
What kind of things do they cover?
Some of them are about implementing the algorithms we discussed.
So like writing the actual code for tree search or tree insert.
Exactly. Others are about analyzing the time complexity of different sequences of operations.
Okay, so figuring out how efficient certain combinations of operations are.
Precisely. And some even ask you to come up with counterexamples.
Counterexamples, so like scenarios where something doesn't work as expected.
Exactly. That's a great way to test your understanding of the rules.
Okay, so the exercises are like a practical way to apply what we've learned.
And then there are the problems, which are more challenging and delve into more advanced topics.
Like what kind of topics?
Well, some of them deal with practical considerations, like what happens if you have duplicate keys?
Ah, right. In the real world, data isn't always perfectly unique.
Exactly. So how do you modify the binary search tree property to handle that?
Interesting question.
Others explore connections to other data structures, like radix trees.
Radix trees, those are also called tries, right?
Yes, they're often used for storing strings.
Okay, so it's like branching out and seeing how different data structures relate to each other.
Precisely. There are also problems that are more theoretical,
Like what?
like analyzing the average depth of a node in a randomly built tree.
So like how far down you have to go to find something on average.
Exactly. That gets into probability and statistics.
Cool. And what was that about Catalan numbers?
Ah, that's a fun one. It's about figuring out how many different binary trees you can make with a certain number of nodes.
So it's like a combinatorics problem.
Exactly.
Wow. So the exercises and problems really cover a lot of ground.
They do. They show that binary search trees connect to many different areas of computer science.
It's not just about the mechanics of the operations, it's about the bigger picture.
Precisely.
Okay, so what about the chapter notes? What kind of insights are hidden there?
Well, the chapter notes provide some historical context, which is always interesting.
Oh yeah, I love a bit of history.
Apparently, the idea of binary search trees was discovered independently by multiple researchers in the mid-20th century.
Wow, so it was really a fundamental idea that emerged in different places.
It was, and the notes also highlight a connection between binary search trees and tries.
Tries, those are the radix trees we talked about earlier.
Exactly, and this connection shows how different data structures can be related in their underlying principles.
So it's like different ways of solving similar problems.
Precisely.
Okay, what else is in the notes?
They also mention an alternative method for deleting a node with two children.
Oh, right, we talked about that complicated process with the successor.
Yes, this alternative is conceptually simpler.
How so?
Instead of moving the successor into the deleted node's place, you just copy the successor's key and satellite data into the deleted node.
So you kind of overwrite the deleted node
Yeah.
with its successor's information.
Exactly. And then you delete the successor, which is easier because it has at most one child.
Okay, so less restructuring of the tree.
Right, but the notes point out a potential drawback.
What's that?
If the satellite data is large or complex, copying it can be inefficient.
Ah, I see. So it's a trade-off between simplicity and potential performance issues. Okay. Anything else in the notes?
They briefly mention the concept of optimal binary search trees.
Optimal meaning like the best possible arrangement.
In a way, yes, but in this context, it means minimizing the average search time.
Okay, how do you do that?
If you know how often each key will be searched for.
So you have some information about the access patterns.
Exactly. Then you can build a tree that's specifically structured to minimize the time it takes to find the most frequently accessed keys.
That's pretty clever.
It is. It's a more advanced topic, but it highlights that there's more to consider than just the shape of the tree.
Right. It's about optimizing based on real-world usage.
Precisely.
Okay, so we've covered the operations, the exercises, the historical context, and now we have the glossary.
Ah, yes, the glossary, a great reference for all of the key terms.
It defines everything from binary search tree itself to things like key and satellite data.
And all the different types of nodes and relationships. Root, left child, right child, parent, subtree.
And the crucial concept of the height of the tree.
Exactly. It also covers the tree walks like in order, pre-order, and post-order.
And all the operations. Tree minimum, tree maximum, tree successor, tree predecessor, tree insert, tree delete.
It even defines the transplant subroutine used in deletion.
And those more advanced concepts like radix tree, lexicographical order, and Catalan numbers.
It's a comprehensive list.
Yeah, super helpful for making sure we're all on the same page with the terminology.
Absolutely.
Well, I feel like we've really explored the depths of binary search trees.
We've covered all the main points from the chapter summary.
We talked about the structure, the all-important binary search tree property, and all those essential operations.
We also discussed the time complexity of these operations, how it depends on the height of the tree.
And we even touched upon those self-balancing variations like red-black trees.
And we delved into the exercises and problems, which highlight both practical and theoretical aspects.
And we gained some historical perspective from the chapter notes.
It's been a thorough deep dive.
So what have we learned? I think the key takeaway is that binary search trees are a really powerful and flexible way to organize data.
They are. They offer great efficiency for a lot of common operations, especially if the tree is balanced.
But we also saw that the order in which data is inserted can really impact performance.
That's right. In the worst case, you could end up with a very skewed tree.
And that's why those self-balancing trees are so important.
They ensure good performance even when the data isn't ideal.
So, final thought for our listeners.
Mm-hmm.
Think about that core principle of binary search trees.
The binary search tree property.
Yeah, the whole idea that everything to the left is smaller, everything to the right is bigger,
It's fundamental.
and it's what makes the search so efficient.
And what guarantees that the in-order tree walk gives you sorted output.
Now imagine if we broke that rule.
If we violated that core principle,
What would happen?
how would it change the behavior of the data structure?
Would it even be useful anymore?
That's something to ponder.
Yeah, something to think about.
It gets to the heart of why this data structure works so well.
All right, and with that thought-provoking question,
We conclude our deep dive.
we've covered everything from the chapter summary, all the major points, the theories, the findings, the examples.
A complete exploration.
Thanks for joining us on the deep dive.
It's been a pleasure.